In this video, we will showcase a universal input 85 volts, 260 volts AC to 12 volts, 3 amps DC Flyback power supply, delivering 36 watts of stable output power. The design uses an affordable PWM controller and an external MOSFET running at 65 kHz switching frequency optimized for efficiency and reliability. The guest and author is Hesam Moshiri, technical writer of Power Electronics News. He holds a master's degree in embedded systems design and is experienced in electronic design and digital marketing. He owns a YouTube channel named MyVanitar that talks about electronic projects and design and measurement tips. So, welcome aboard, Hesam.
Hi friends, welcome to Project Time. This is an AC to DC flyback converter board. Here is the AC input, universal in the range of 85 to 260 volts. And here is the DC output, 12 volts, 3 amps maximum continuous. It means 36 watts of power maximum continuous. Let me show you the board from different angles. The back side. These are the isolation gaps or creepage areas. I explained the schematic and I will point the components on the PCB. So here is the AC input. It goes through this fuse, this orange component for protection, of course. R2 is a varistor, this one, to protect the circuit against possible high voltage transients. C1, this yellow component is an X2 rated capacitor for noise reduction. R1, this one, is an NTC to limit the startup inrush current. T1, this one, is a common mode choke for noise reduction. BR is a bridge rectifier to convert the AC to DC, of course. And C2, this fat guy, is the main capacitor for ripple reduction. Use a high quality capacitor for C2, otherwise it might dry out too soon. It should work at least for 7, 8 or even more years continuously. The high voltage DC line goes through this RCD snubber, these 3 components, and one side of the primary of the transformer. Another side of the primary is switched by this MOSFET, this one. This MOSFET is rated 650 volts, and this RCD snubber is to ensure or is to protect this MOSFET against high voltage spikes and transients on the primary here of the transformer. Also, it has a good effect to pass the conducted emission and EMI test if it is designed correctly. You can either use 2 resistors in parallel or a single 2 watts resistor, 47K resistor, the same as me. Here is the controller to switch the MOSFET, and the switching frequency is 65 kHz. Let me show you the controller. This one is the controller, and this one is the current sense resistor to detect any short circuit or overcurrent. This one. Let's go to the auxiliary side. Here is the auxiliary winding of the transformer. It goes through these components to convert the AC to DC and to reduce the noise of the auxiliary. These 2 resistors provide the initial startup current, these 2, for the controller, these 2 resistors. And because the initial startup current of this controller is low, I think it is around 30-40 microamps or so. So the package size of these 2 resistors is small, and also the resistance is high. Otherwise, we should use a high power resistor for the startup. This is an advantage for this controller. After the startup process, the auxiliary winding supplies the controller. So here is an RC filter to reduce the noise, and this Zener diode, this one, ensures that the voltage on the supply of the controller here does not go higher than 24 volts, because when the input voltage, the AC input, is high and you draw high current from the output, naturally the voltage on the auxiliary winding also increases, and this Zener diode ensures that this voltage does not go higher than 24, otherwise it will activate the protection feature of the controller and it turns off the power supply. However, because the current consumption of the controller is low, a simple Zener diode is enough. This capacitor, this one, I'm not sure if you can see, is in parallel with this capacitor, because this capacitor also is prone to failure and drying out, and a capacitor in parallel, 100 nanofarad capacitor, reduces the total ESR and increases the lifespan of this capacitor, because if this capacitor dries out or it fails, it affects the performance of the supply, or the supply will stop working. This resistor is recommended by the datasheet to fix the switching frequency on 65 kilohertz. Let's go down. This optocoupler, this component, provides a galvanically isolated path for the controller to sense the output voltage and modify the duty cycle of the primary, the switching duty cycle, and modify that duty cycle to regulate the output. It is more complex than this, but a simple explanation is what I said. Here is the output. This Schottky diode to convert the high frequency AC to DC, and this Pi or CLC filter to reduce the noise, these components. Okay. This resistor is a dummy load, this one, to stabilize the output, and this LED, this one, shows that we have a voltage at the output. This is a Y capacitor for noise reduction and protection, of course, this one. And this multi-term potentiometer is to compensate the tolerance in winding the transformer, because naturally for prototyping people make the transformer by hand and it will have some tolerance. So this multi-term potentiometer is to compensate that tolerance. I think I covered everything. Let's go to the back side. You can see this ground plane is almost a solid. It's almost a solid ground plane to reduce the length and impedance of the ground path. The result is more stability and lower noise for the power supply. And this is the shunt regulator, this one, to regulate the outputs. So that's it for now. Let's go to the next step. Alright, I have prepared this picture to show you what type of ferrite core and bobbin you should buy. Also, the winding pattern of the transformer. If you look at the left picture, you should buy this ferrite core, EFD25, and this bobbin. You can find exactly the same ferrite core and bobbin on the market, so no problem with that. The winding pattern also is pretty obvious. For example, these two pins is the primary winding, these two auxiliary winding, and you can find the specifications of the secondary winding on the right side. For example, the primary winding is made of 56/10 of 0.4 mm of magnet wire. This is the gap size, mathematical calculation, and you should play with the gap size till you reach this inductance in the primary. My assumption is that you know how to wind the transformer, especially for prototyping you will wind by hand, I think. By the way, don't forget two things. Wrap 2 or 3 layers of transformer tape on the primary after you finish the primary. Also use heat shrink on the wire ends of the primary because high voltage isolation is important in such a small transformer. By the way, that's it for transformer. Let's go to the next step. Alright, welcome to the table again. I have prepared the setup to test the power supply board. Here is the AC input and this side is the DC output. You can see the LED lights up and the output is connected to this DC load. The output voltage is 12.027. So for the first test, I will apply the maximum load, which is 3 amps, to the output, and we will examine this number to see how good or how tight is the regulation. So I set 3 amps on the DC load and I will turn on the output. 1, 2, 3. So just 4 or 5 millivolts voltage drop at the maximum load. A big thumbs up for this power supply indeed. For the next test, I will examine the spikes and ringing on the primary of the transformer. Alright, I have connected the oscilloscope probe, channel 1, to the drain of the MOSFET and the ground lead of the probe to the input ground. For this purpose, you should either use a high voltage differential probe or power your board using an isolation transformer. The board, your device and the test. In my case, I don't have a differential probe, so I use an isolation transformer. And by the way, this is the waveform when there is no load at the output. So it says the peak-to-peak voltage in this condition is 470 volts. But what happens when I apply the maximum load, which is 3 amps, to the output? 1, 2, 3, and there we go. This is the waveform. Now it says the maximum peak-to-peak voltage is 510 volts maximum, or 500. This is well below the maximum drain source of the MOSFET, which is 650 volts. So the snubber does the job and it is pretty acceptable, but it is better that we don't see any sharp edges on this ringing here. It is pretty important to pass the conducted emission and EMI tests. So let me play with the volts division knob and examine this ringing here. And as you see, I don't see any special ringing, sharp edges on this ringing. You may ask why the waveform is like this. This is the jitter feature of the controller and is used to reduce the EMI. It's not a problem. So I don't see any sharp edges on this waveform. So the snubber does the job perfectly and this power supply is a really good design. So I hope you like this project. Don't forget to share and subscribe. We will do something else in the next video.